Hi, good morning, good afternoon, good evenings to all of you. My discussion for today will be about elementary particles and fundamental forces. Elementary particle physicists seek to answer questions like how it is that our universe came to be so rich and varied, and why are there stars, sun, sun, planets, and 100 different atoms that can be combined to form immeasurable molecules. These questions can be answered by studying subatomic particles and forces. In fact, the properties and interactions of the elementary particles have much to say about the properties of the world around us. In the literal sense, nothing is simpler than an elementary particle, only if there is no proof that a particle is made up of smaller constituents, then it is classified as elementary. Identifying elementary particles, discovering their properties, and observing their interactions, on the other hand, is turning out to be the secret to understanding why the world is the way it is, how it came to be this way, and what its ultimate destiny would be. About 100 years ago, atoms were considered elementary particle until physicists learned that atoms consisted of electrons orbiting a nucleus. Although atoms were thought to be elementary, they too are are composite objects. So the atom, as first revealed in experiments by Rutherford, is an electrically neutral object, approximately 10 billionths of a centimeter in diameter. This means that there are about 2 million atoms stretching across the diameter of the period. Each atom has a tiny positively charged nucleus about 10,000 times smaller, and the negatively charged electrons occupy the space surrounding the nucleus. In 1987, Joseph John Thomson discussed that the mass of the electron is about 2,000 times lighter than the mass of the hydrogen nucleus, the proton. So this led the electrons to become the first ever modern elementary particles to be discovered. The mass of most nuclei is about twice the mass of the protons they contain. The additional mass is provided by another particle, which is neutron, and has a very close to proton. Has a mass that is very close to proton, but is electrically neutral. And elementary particles are the smallest known building blocks of the universe. They are thought to be they are thought to have no internal structure, meaning that researchers think about them as zero-dimensional points that take up no space. While elementary particles are smaller than a grain of sand in comparison to the entire Earth, their properties have enormous consequences. If the electron, for example, had been much heavier, the universe would have formed very differently. There would be no atoms, and the universe would now be made up entirely of electrically neutral particles, and there would be no stars to gaze at, and no one to ponder the universe's origin or ultimate destiny. So the key to understanding the properties of elementary particles is the description of the forces of nature in which they participate. So before I introduce to you to the various elementary particles, let me first address the fundamental forces, or also known as fundamental interaction. So these are set of forces that control how objects or particles interact and how those particles decay. So please note that all particles in nature are subject to four fundamental forces: the strong, the electromagnetic, the weak, and gravitational forces. These forces can be characterized based on the types of particles that experience force, the relative strength of the force, the range over which the force is effective, and the nature of the particles that mediate the force. Remember that the weak and strong forces are effective only over a very short range and dominate only at the level of subatomic particles, while the gravity and electromagnetic force have infinite range have infinite range. So let's see each of them in detail. The first fundamental force is the strong force. The strong force is responsible for the tight binding of quarks. So quarks is a type of elementary particle to form neutrons and protons, and for the nuclear force, a sort of residual strong force. As I've said, binding the neutrons and protons into nuclei. It is responsible for holding the nuclei of atoms together. It is basically attractive but can be effectively repulsive in some circumstances. The next fundamental force is the electromagnetic force, which is that's actually 10 to the power of negative 2 times the strength of the strong force. It is responsible for binding the atoms and molecules. It is a long-range force that decreases in strength as the inverse square of the separation between interacting particles. The electromagnetic force causes electric and magnetic effects such as the repulsion between like electrical charges or the interaction of bar magnets. It is a long range but much weaker than the strong force, and it can be attractive or repulsive and acts only between pieces of matter that carries an electrical charge. Electricity, magnetism, and light are all produced by the electromagnetic force. Another force is called weak force, and it is short-range nuclear force that is exhibited in the instability of certain nuclei. It is involved in the mechanism of beta decay, and its strength is only about 10 to the power of negative 6 times than the strong force. Weak nuclear forces are responsible for the radioactive decay, specifically the beta decay neutrino interactions. The properties of weak force are as follows. 1. Weak nuclear force is the only force which does not follow parity symmetry. Second, it is the only force that does not follow charge parity symmetry. Third, weak nuclear force is responsible for the change in quark into other forms, and carrier particles with significant masses are responsible for the propagation of the weak force. But remember, guys, it doesn't mean that it is called weak. It is already the weakest among the four forces. Since the weakest of them all is the gravitational force, which is the last type of the fundamental force. This gravitational force explained as the force that attracts any two objects with mass. So, normally the question here is, why is the universe not filled with floating human beings and cows and cars and other such things? Obviously, because the gravitational force of the earth holds us to the planet. So gravitational force is the one who is responsible for holding planets in their orbits. And this is possibly only because of their infinitely long range. It is also the attractive force which arises from the gravitational interactions. And according to Newton's law of gravity, the gravitational force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. So when we considered massive objects like sun or giant planets, gravitational force is considered to be strong as the masses of these objects. So on atomic level, this force is considered weak. Next is the fundamental force particles. In the language of modern physics, the electromagnetic force is carried by photons, which are considered as the quanta of the electromagnetic field. The strong force is carried by the particles called gluons. That is, when two particles interact through the strong force, they do so by exchanging gluons. While they are close together, the quarks will experience little force. But as they separate, the force between them grows rapidly, pulling them back together. So to separate two quarks completely would require far more energy than any possible particle accelerator could give or provide. Thus, the quarks inside of the protons and neutrons are bound together by the exchange of the strong nuclear force. On the other hand, the weak force is mediated or carried by particles called the W and Z bosons, while the gravitational force is thought to be mediated or carried by quanta of the gravitational field called gravitons. So to sum up their forces, the gravitational force is considered as the weakest force but has infinite range. The weak nuclear force is the next weakest but short range, and the electromagnetic force is stronger with infinite range, and the strongest of them all is the strong nuclear force but has a short range. And the forces between two particles are delivered by or conveyed by an exchange of field quanta. So this process is just similar to the covalent bond covalent bond formed between two atoms when electrons are exchanged or shared. A basic example called a Feynman diagram created by Richard P. Feynman. Feynman can be used to understand the force between two particles in general. So the figure below is an example of a Feynman diagram, and you can observe that the electromagnetic interaction between two electrons is depicted. A photon is the field particle that mediates the electromagnetic force between the electrons in this simple example. In the interaction, the photon transfers energy and momentum from one electron to the other. Since it is absorbed by the second electron so quickly after being released by the first electron, such photon, known as virtual photon, can never be observed directly, while the presence of virtual photon would seem to violate the law of conservation of energy. It does not due to the time, energy uncertainty principle. So if the simulated photon exchange occurs rapidly enough, the energy conservation difference is less than minimal uncertainty in energy, and the exchange is physically acceptable. Before proceeding to the discussion of elementary particles, let's have first the theory of Paul Dirac. Dirac claimed that in every particle there is an antiparticle with the same mass as the particle but the opposite charge. So an antiparticle is usually designated by a bar over the symbol for the particle. So practically every known elementary particle has a distinct antiparticle, but there are some exceptions like the photon and neutral pion, which have their own antiparticle. So an antiparticle is not identified solely on the basis of opposite charge, because even neutral particles have antiparticles. So this idea led to Carl Anderson's discovery of positron. He discovered it through cloud chamber experiment. He used a magnetic field to cause moving charges to follow curved paths, allowing him to distinguish between positive and negative charges. Then he found out that some of the electron-like tracks shifted in a direction that corresponded to positrons, which are positively charged particles. But the question is, how are particles classified? All particles other than those that transmit forces can be classified into two broad categories. First is the hadrons and second is the leptons, according to their interactions. Leptons, from the Greek word leptus, meaning small or light. These are a group of particles that participate in the weak interaction. So particles that interact through the strong force are called hadrons. So the two classes of hadrons known as mesons and baryons. These can be distinguished by their masses and spins. So some of the important properties of hadrons are listed in the table here. In the table, all leptons have a spin of 1/2. Included in this group are electrons, muons, and neutrinos, which are all less massive than the lightest hadron. A mu1 is identified to an electron except that its mass is 207 times the electron mass. Although hadrons have size and structure, leptons appear to be truly elementary, with no structure down to the limit of resolution of the experiment. All mesons are known to decay finally into electrons, positrons, neutrinos, and photons. A good example of meson is the pion, which is the lightest of the known mesons. Baryons, on the other hand, are heavy subatomic particles that are made up of three quarks. Both protons and neutrons, as well as the other particles, are baryons, and their spin is always non-integer value. So now we are down to our last slide, which is about the standard model of elementary particles. The picture may look complicated, but it is actually organized in a way which makes it very easy to understand. And the name may seem like so dull, like standard model, but it really simplifies the greatest piece of scientific achievement. Why? Because the standard model is the description of the basic building blocks of everything in the world. I mean, in the universe, rather. So, this standard model enabled us to understand how this universe of ours is built. So, I will explain it to you one by one. There are actually two types of particles. We have fermions and bosons. Fermions are arranged on the left side while the bosons are on the right side. Let us begin first on the right side. Bosons are particles with integer spin values of 0 or 1. There are two types of bosons. Depending on the spin value, the gauge and scalar bosons are generated. The spin value of gauge bosons is 1, while the scalar boson is 0. The gluon, photon, W and Z bosons are the four forms of gauge bosons. The exchange particle for strong force are gluons. Photons are the electromagnetic interactions or force exchange particles, and the exchange particles for weak interactions are the W and Z bosons. The charge of W boson is either negative or positive, while the Z bosons are electrically neutral and have no charge. So please take note of that. Scalar boson, the only particle belongs to scalar boson is the Higgs boson. Take note that Higgs boson is the most recent elementary particle added to the list of elementary standard model of elementary particles. It is the quantum excitations to Higgs field. Unlike other fields, such as electromagnetic field, Higgs field has non-zero value in vacuum. Higgs field is responsible for providing intrinsic mass to particles. Until now, we have seen elementary particles responsible for 3 out of 4 fundamental interactions, which is the graviton. I've mentioned this earlier. The graviton has no boson. Graviton is a hypothetical boson that known to be massless, chargeless, and have a spin value of 2. However, it is believed to be the exchange particles for gravity. Even so, it would be unlikely to detect graviton since gravity is many times weaker than the other fundamental forces. That is the reason why graviton is not present or could no longer be seen in the standard model of elementary particles. Fermions, on the other hand, are elementary particles with half-spin values. Quarks and leptons are the two types of fermions, which are categorized based on their interactions. Both quarks and leptons are further classified into three generations depending on their masses. Quarks are the fermions which experiences all four fundamental forces: the strong, electromagnetic, weak, and gravitational. The interaction with the Higgs field gives quarks their intrinsic mass. Only composite structures like the proton and neutron contain quarks. There are 6 different types of quarks, each of which is divided into 3 generations. Generation 1 are up and down, which are considered to be least massive and most stable. Generation 2 are the charm and strength. And the generation 3, top and bottom, which are unstable and rapidly decay into up and down quarks. Sorry for that interruption. So, as I have said, generation 3 consists of top and bottom, which are unstable and rapidly decay into up and down quarks. So, higher generation massive quarks are produced during high energy collisions involving cosmic rays or inside particle accelerators. Leptons are the fermions which experiences only 3 out of 4 fundamental forces. Unlike quarks, leptons do not experience strong forces. So therefore, they can exist freely in isolation. The intrinsic mass of leptons comes from interaction with Higgs field. The same with quarks, there are 6 types of leptons divided into 3 generations. The generation 1 are electron and electron neutrino, which are considered to be least massive and most stable. Generation 2, mu1 and mu1 neutrino. Generation 3, tau and tau neutrino, which are unstable and rapidly decay into electron and electron neutrino. So, higher generation massive leptons are produced during high energy involving cosmic rays and inside particle accelerators. So, lastly, let's talk about the antiparticles. Please note that only fermions have antiparticles, since bosons either don't have antiparticles or they are their own antiparticles. So, antiparticles of quarks are called antiquarks. Same magnitude, opposite charge. So, it will be like anti-up, anti-down, anti-charm, anti-strength, anti-top, anti-bottom. So, antiparticles of leptons are called anti-leptons. The same magnitude and opposite charge. It will be like positron electron antineutrino, anti-mu1, mu1 antineutrino, anti-tau, and tau antineutrino. So that's all about elementary particles and fundamental forces. I hope that you have learned at least a little bit from what I have discussed. So thank you so much, guys, for listening.